All right, everybody, let's get started. So, let me pull the screen down a little bit, make it a little bit easier to see, and scan the attendance code if you haven't already done so. Just so you're aware, what I'm going to do in Blackboard on days that we have lab like today is I'm going to count the attendance twice. So, once for class and once for lab. So, if you see, like, today showing up twice, you'll understand why. That's why I'm doing that. A couple housekeeping items. So first off, lab groups. I've assigned lab groups today, and I'm going to show you my very scientific method for how I assigned lab groups. So there are 29 students in the class, right? So what I do is I go to Excel, and I use what's called the rand function to generate a random number, okay? And I basically just go big money, big money, big money, Noemi, 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 stop. And then I say, okay, we're going to take these values, we're going to lock them in, and then what we're going to do is we're going to sort this table by the second column, and that's the lab groups. So, very scientific, but that's how the lab groups got assigned. So yeah, that's it. So your lab groups have been assigned. Also in Blackboard, there are lab groups assigned inside Blackboard, and so there are certain lab assignments that you're going to submit via Blackboard, and the way that it'll work. So we're going to have some labs that are going to be individually graded, some that are going to be graded as a group. So like today's lab is going to be graded as a group. And so what we'll probably do is set it up to where you can scan it and just submit it via Blackboard, and any one person in the group should be able to submit. But when you see the lab today, as long as you essentially do it and whatnot, you should receive full credit. And we're going to talk about that here in a second. Okay, before we get into the, like what we're going to do in lab today, because I'm actually going to talk about that first before we get into the lecture. First off, the lab assignment, the safety quiz was due today. Did everybody get that done? Good. Okay. Homework assignment. We have a homework due Thursday. Has anybody taken a look at it? Anybody have any questions? Does it seem challenging? Is everybody thinking Thursday at 12:30? That's a Thursday at 11:30 a.m. problem, Dr. Mike. What are you talking about? I know things about stuff, but I know how it goes. But in all seriousness, any big questions? Okay. All right, before we get into the specifics of the lecture today, I want to talk a little bit about the lab. And it's going to be a really short lab, but I do think it's kind of a nifty one. So I'm going to give you these handouts here in a little bit. But just to explain what we're doing today, I have in the lab, like I said, it's going to be a very quick lab. I have in the lab 7 boxes, okay? And those boxes are each filled with a specific material, okay? So I've got one box that's filled with coal, one box that's filled with wood, one box that's filled with concrete, etc., right? Then I've got loose aggregate, loose soil, dense aggregate, dense soil, okay? What I want you to do are 3 exercises, okay? Exercise number 1, without touching the boxes, without weighing the boxes, I want you to just use your best judgment. Use what you think you know about the materials, no Google, no nothing. Just tell me in what order would you rank them in terms of what material is heaviest, what material is lightest, okay? I want you to give me some reason why you're doing that as a group. And so you all as a group can get together and discuss that. But the key with exercise number 1 is I don't want you to touch them, I don't want you to weigh them, I don't want you to Google them. Just internally within your group, rank them and tell me why, okay? Everybody with me on exercise 1? Okay. Exercise number 2, I want you to list them, okay? And I want you to list them as a group and then see if your ranking changes, okay? Now some of these boxes are kind of heavy, so, in fact, most of them are kind of heavy. So it's probably going to be a 2-person list, and, if there's anybody in your group like that's too heavy, just let us know. We'll do some substitutes and whatnot. We obviously don't want anybody to get hurt or anything. They're not that heavy, but if you lift them by yourself, they're a little heavy. Each of the boxes are 1 cubic foot, so they're about like this, okay? And they have handles on each end, so they're not terribly difficult to lift and whatnot, but just be careful when you're doing that. And so exercise number 2 is you lifting them and seeing if you can record. And then exercise number 3 is actually weighing them, okay? Now, the thing with the weight is when you weigh it, you're weighing the material and the box, okay? I have an empty box that I weighed, and the empty box weighs 11 pounds. The reason for the empty box is because in the past there was an 8 material, and the 8 material was water, okay? But it's kind of messy because it kind of spills all over the place. So I just decided to dispense with the water. So like what you would do is, okay, so like each box is 1 cubic foot and the box weighs 11 pounds. So if you had a reading of, let's say, 82 pounds, I just made that number up, then the actual unit weight would be 82 minus 11 divided by 1 cubic foot, or just 82 minus 11. So like what you would do in these boxes right here is just record them as, you know, 82 minus 11 equals 71. 115 minus 11 equals 104. Does that make sense? So that way, so just like put your actual reading minus 11 equals something, okay? And then at the bottom, you know, a few statements on, you know, what you thought about the lab, anything that surprised you, anything you learned during the lab, and that'll be the lab, okay? So it's that instead of like a full-blown lab report, okay? Some labs, we will have a full-blown lab report, but not for this one. This one's just to get us familiar with the space and get us used to doing stuff in lab this semester. Okay, does anybody have any questions about that? Everybody good? Okay, so that's what we're going to do today. One thing I will say about labs, so this class meets from 12:30 to 1:45 p.m., and then we have lab at 2 p.m. Okay, so there's technically a 15-minute gap in between. What I'll say is that there are some labs we might take the break. I don't know about y'all, but I say today, let's just end class, go right down to the lab. I mean, because we're not going to be in lab very long. There are some labs, though, that actually are going to kind of be a little bit long, and I know this might seem counterintuitive, but I actually think it's a good idea to take a little bit of a break so that we can go do the experiment. Namely, the concrete lab, when we do that, that is going to take a good bit of time, so we might as well, if we're going to take a break, let's take a break, and then let's knock it out, okay? Does that sound good? This lab will be, I don't see us in there past 2:30, 3 o'clock. We'll be there pretty quickly. All right, sound good? Okay. All right, so any questions about logistics, any questions about what we got going on here? Okay, now the only other thing I wanted to mention before I bring it to the discussion today is that I've made a request for everybody in the class to have key card access to the lab, the actual room with the lab, from now to the end of the semester. There will be a couple of labs where we're not going to be able to collect all of the data there in the lab. We'll actually have to come in the next day or the day after to collect the data. That'll become clear why I'm saying that actually during this lecture, okay? So we'll get to that here in a little bit. But if we have lab on Tuesday, you may have to come in like someday on Thursday or Friday and collect a little bit of data. Again, it'll be clear why I'm saying that here in a bit. Okay, everybody good? All right, I will say, by the way, if you pull up Blackboard now, you'll see a section on aggregates, and there is oodles of stuff in that section of aggregates. I've got lecture notes, I have some charts that we're going to use, namely a gradation chart and an aggregate blending chart, and I also have ASTM testing standards. Between today and the next 4 lectures, we're going to discuss all of that. I will say some of the lectures, like there's not a whole lot of consistency in terms of slide length. Like this one has like 30-some slides, and then there's one lecture that only has 5 slides. So, but between today and this lecture and the next 3 lectures, these 4 lectures, we'll cover in completion the topic of aggregates, okay? And so today our focus is just an overview, and we're going to talk about moisture states and unit weights, okay? Everybody good? All right, did everybody get the code one last time? Okay, all right, so let's pull up the lecture and let's talk a little bit about aggregates, okay? And so aggregates are one of the most fundamental civil engineering materials that we use as civil engineers. And I should preface this lecture because I was going through the notes and I was sort of thinking about what I would say, and I found myself going through the notes saying, okay, and here's this. By the way, this is going to come up later. And I would say, oh, here's this term. We'll talk about this later, or we'll bring this up later. Mainly, I'm going to be saying that a lot today is because aggregates tend to serve two main purposes in civil engineering. One of them just as a construction material themselves, but also as an ingredient for other materials like asphalt and concrete. So I'll bring up stuff and then I'll say, this is going to be important later when we talk about concrete, or this is going to be important later when we talk about asphalt. So you're going to hear me say that a lot when we start discussing aggregates. So I'm just prefacing that because we'll mention that. Okay. So like I said, aggregates tend to serve two main purposes. That is as an underlying material in foundations or pavements, and as an ingredient in either Portland cement concrete or asphalt concrete. We don't typically refer to them as rock or stone in like engineering context, though probably on a construction site you will hear somebody refer to that. Has anybody, for example, heard the term number 57 stones? Anybody ever heard that before? So we'll actually bring that up, like what number 57 stone actually is. You'll be able to define what that is here in the next few lectures, because there's a specific specification, ASTM C33, that will explain what that is. So, okay. Where do you get aggregate? From the earth, mostly, and so, bless you. So natural source would be like natural sand and gravel pits, quarries, and whatnot. We are in the mountain state, so not too terribly difficult to figure out where we would get aggregate from in a place like this. You can also source aggregates from manufacturing sectors, from recycled materials. So aggregate may be things like old concrete that's been pulverized, things like slag from steel mills, expanded shale, and whatnot. Those are other sources of aggregates that you can see used. More often than not, like your primary source of aggregate is just going to be the earth. So quarries, you know, sand pits, gravel pits, things like that. Okay. Okay, where do you get, well, let me just say this. Aggregate is, again, its source is rock and stone from the earth. I'm not going to say a whole lot about like the geology side of things. Really, any of the three classifications of aggregate, igneous, or of rock, you know, igneous, sedimentary, metamorphic, any of those would be just fine sources of aggregates. They're all fine for civil engineering applications. Usually what I would tell you, or tell any civil engineer, is that, you know, if I was designing a bridge in, let's say, West Virginia, and then I'm suddenly designing a bridge in Hawaii, the aggregate is probably going to have slightly different properties, like chemical properties, physical properties, and whatnot. And the best source of how it's going to perform is just historical performances and similar designs in the area. So that's probably really the only thing that needs to be said on that. Okay. All right. Now, one set of terms that I am going to say is entirely proper to use in a civil engineering context is the terms gravel and sand. Okay. So those are really the two main classes of aggregates, whether or not we're dealing with a gravel or whether or not we're dealing with a sand. Okay, what is the difference between a gravel or a sand? Or more specifically, how do we classify the gradation of aggregates? Well, we do that using sieves, okay? And of course, I come up here and I forget the sieves. So we have tons of sieves in the lab. I'll show you some sieves today. But the sieves that we use, basically what we'll do is we'll set up a series of sieves and we'll pour the aggregate on top and then agitate the sample and then determine how much material is retained on each sieve, okay? And so sieves go from having really, really big openings, so you can see the openings between the wires. Sieves go from having openings that might be like 6 inches wide, so, you know, an aggregate that has, you know, like that, to having particle openings that are in the 0.005 millimeter range, where you don't even really see the openings. It just sort of looks like a fine cloth and whatnot and everything in between, okay? Now, what we do, and we'll talk a little bit more about sieves here in a bit, but we classify sieves either based on the opening, or the size of the opening, or the number of openings per inch. So a number 4 sieve has 4 openings per inch, and some of you might be thinking, well, isn't that just a quarter of an inch? Not really. It's less than a quarter of an inch because you have to account for the thickness of the wire. So a number 4 sieve is the dividing line that we use as civil engineers to define whether or not an aggregate is a gravel or a sand. Okay? So if I have a number 4 sieve, if the material falls through the number 4 sieve, it's a sand. If it's retained by the number 4 sieve, it's a gravel. Okay? And it's the number 4 sieve, that's the dividing line that we use as engineers to define the difference between a gravel and a sand. Okay? It's the number 4. So it's not like I'll ask you that on a celebration or anything. They're getting it. They're picking it up. Okay. So here's just, I mean, this is sort of what I'm talking about, gravel and sand. Notice that on the slide here showing images of the gravel, you can see that these 2 gravels have different properties, okay? For example, I mean, so like, what do we see different between these 2 gravels? Number 1, the color, although we don't really care about that more often than not when we're mixing concrete. It doesn't really matter what the color is. But does anybody notice something else that's different between the coarse aggregate samples that we see here?
One came out of a stream.
One looks like river rock, so you can see the particles are much more rounded versus this one that's angular, okay? The surface characteristics of the aggregate do have an effect on its performance in a concrete, okay? And I think I'll mention this a little bit later, but angular particles tend to provide more strength and stability in a concrete mix, whereas rounded particles add a little bit more workability to the mix. The mix is a little bit easier to work around, but with that increase in workability, you get a sacrifice in strength and stability, and vice versa. Like, this is much stronger, it's a little bit more difficult to work with. So, you know, there's a trade-off there. So, just something worth mentioning. Sand's a little bit more tough to see with the naked eye and whatnot. So, but yeah, sand is sand. Okay, so like I said, part of the performance, or the gradation, if you will, of an aggregate is determined using sieves, okay? And so we'll have at least 2 experiments in the class where we do what's called a sieve analysis. And so what we'll do is have a stack of sieves. The sieves will get smaller and smaller, and then at the very bottom we'll have a pan to collect whatever's left over. And so, for example, if we're doing a gravel, we'll have larger sieves. You know, if we look at larger sieves, you know, we'll have like maybe 3, 2.5, 2, all the way maybe down to a quarter of an inch. And then smaller sieves and whatnot are designated by sieve number. Okay, so for example, if I have the number 30 sieve, that means there's 30 openings per inch. Okay, so you can get kind of an idea as to how small these are. Probably another noteworthy sieve worth mentioning is the number 200 sieve. Is there anybody in here that's already had geotech? Did the number 200 sieve come up a little bit? Why did it come up? It discretized the difference between a sand and a silt. Anybody remember that? So in soil mechanics, we have gravels and sands that we consider as well, but if you have the number 200, those are fines. Anything smaller than that we consider a silt. Do y'all know what I'm talking about? Okay, good. It came up? I hope it did. Oh, did it come up?
Yeah.
Did it come up? Okay. I hope everybody's shaking their head yes. Okay. Okay. So like I said, again, the openings are a little bit smaller than on the numbered sieves than, you know, if it's 4 openings per inch, it's not quite a quarter of an inch, it's a little bit less. Like a number 4 sieve, the opening is 4.75 millimeters. And as you start getting really, really tiny, the openings, of course, get much tinier and whatnot. Okay. All right. So one thing I'll mention, and again, this is one of those points that will come into importance later. We'll do an example in here with this, I believe, on Thursday, where we do a gradation analysis. But we do have some terms that we'll define as a maximum aggregate size and then a nominal max aggregate size. And I'll say for now, just keep these terms in the back of your head. It's not really going to be very important today. But what I'll say is that the nominal max aggregate size is typically the first sieve to retain some aggregate whenever you do a sieve analysis. and that's the nominal max aggregate size. The maximum aggregate size is sort of 1 sieve larger. Keep in mind, when you perform a gradation analysis, you're doing it on a representative sample of aggregate and not the entire stockpile, okay? So that's why we might have the two classifications. This is traditionally what we define as our maximum sizes and our nominal max aggregate sizes. When we look at what's called super pave is a specific design method for asphalts, for pavements. The difference between here and here is 1 size larger. So the idea that this and this are the same, if that makes any sense. But again, those are just items to keep in the back of your head a little bit later when we do some examples or discuss asphalts a little bit later. Okay. So like I said, where do we use aggregates? We tend to either use them as a specific material themselves or as an ingredient. For a material themselves, they tend to be used as a base for foundation installations or for pavement installations, mainly because they provide stability and they also allow for drainage. Okay, they allow water to permeate through the base and whatnot. For that reason, they also tend to be used quite a bit behind retaining walls. Okay, if you've ever installed a retaining wall, maybe in your backyard, you probably use some crushed up stone as a base or behind the wall to allow for drainage and whatnot. So that they tend to perform very well there. But beyond that, the two really big important uses of aggregates are in concrete and asphalt. Okay, they are for both applications. Aggregates are the primary ingredient by volume and weight. They're certainly not the primary ingredient in terms of chemistry, I guess you could say, because, I mean, in the case of concrete, it is the cement, the Portland cement, that acts in congregation with water as the binding agent that binds everything together. But in terms of volume and weight, aggregate is the star of the show. So in a typical Portland cement concrete, the aggregate consists of about 70 whatnot % of the volume and about 80 whatnot % of the weight. And in hot mix asphalt, it's even more. The aggregate is by and large the star of the show for volume and weight. But yeah, we really concrete and asphalts get their strength from their aggregate. It's the aggregate that's resisting a lot of the compressive forces and whatnot. And aggregates a lot. It's really something that you do want to include more often than not. I mean, when you include more aggregate, you get cheaper mixes, and you also get higher strength mixes. So aggregate's really where the behavior comes from in terms of mechanics. Okay, everybody good so far? All right. Now, I could go on and on about the various properties of aggregates. Some of them are important, some of them are not. And we can have, I mean, I want to be clear, there are students who get entire degrees in material science, okay? You are getting a degree in civil engineering. So what I'm focusing on are the properties that that are of most import to you as civil engineers, okay? But I want to be clear, there's all sorts of other properties of aggregates that may be important or not, dependent upon your application, okay? We're going to discuss the ones that kind of make sense to us. And what we're really focusing on for the purposes of engineering computations are these three right here: moisture state, specific gravity, and gradation. It's not to say we're not going to talk about the others. For example, we'll talk about shape and texture. And is shape and texture important? Well, yeah, it's important. We're going to have labs on that. But in terms of computations, these are the three that are important. Your textbook has some characteristics that may or may not be important dependent upon your mix or dependent upon your application. So, like, let me give you an example. I have here a table that shows physical properties, and then the following slide shows chemical and mechanical properties. Like, for example, what is the importance, if you will, of the integrity during heating of an aggregate? Well, if we're talking about Portland cement concrete, not very important, okay? Do we really care about how an aggregate behaves under heating when replacing concrete? Not really. Now, why is it a little bit more important for asphalt? Well, because asphalt is placed as a hot mix, right? So it's going to be hotter, right? So it's a little bit more important for an asphalt than it is for a concrete. What about for a base? We don't really care, okay? But that being said, some of the other properties are very important. What about particle size distribution? What about pore structure and porosity? Okay, here's a good one. Why is pore structure and porosity? What about specific gravity and absorption? Why are they very important for Portland cement concrete? Well, what we're talking about with those properties is the ability or the tendency of the aggregate to absorb water. Kind of important when you're mixing concrete to understand the moisture characteristics of the aggregate before you start mixing your concrete. The more water you pour into your concrete mix, the weaker it is. So you kind of need to understand that stuff. So that's going to be the kind of stuff we talk about in here. And that's just your chemical properties and then your mechanical properties. So I'll just, again, I'm just going to skip past this because, I mean, they're in your textbook. I'm just sort of mentioning, I'm going to mention the same thing here on this slide as I mentioned on the previous one. Okay, we will have a lab a little bit later where we look at the particle shape and surface texture and characterize whether the particles in a given aggregate are angular, whether they're rounded, whether they're elongated, whether they're flaky and elongated. What am I talking about here? Well, when I say angularity, I'm talking about essentially how sharp or angular are the individual particles. The more, and I had kind of already talked about this, but the more angular a particle is, that means it has higher strength and higher stability. The more rounded it is, it has more workability. Okay. So an example of where you might find rounded particles is at the beach, okay? So here's sort of like the idea of what I mean by a rounded particle. Has anybody ever been like in a ball pit at McDonald's or someplace like that? So like if you have they just slide against one another, right? You are standing, you can pretty much just walk right through it. It's not really providing much resistance. Now think of if you were to include particles like that in a concrete mix. It'd be very easy to work around, but it wouldn't provide much strength, you know. So that's sort of the trade-off that you get. Okay. So just something to keep in mind when you're classifying materials. What about its flatness and elongation? This is kind of important because, if, for example, if you had particles that were really flat and really elongated, they might lead to easy breakage because you have really, really thin particles that are really long. And that could cause a problem if you're trying to compact this material as a base for a foundation or a road, because every time you're compacting it, the particles keep breaking. So understanding that could lead to, you know, a better understanding of how long it's going to take on a given construction project to compact the material and so on and so forth. And so this is going to be something else that we also classify in an experiment. I believe it's maybe not next week or the week after. So. Okay, I won't say too much about this, but I'll say that for the purposes of some of these classifications, a lot of it is visual in terms of the number of fractures, the size of the particles, and so on and so forth. One thing I will mention: we're not going to do every experiment in this class that we could on every particle. I mean, some of the experiments I'll mention, some of them I'm going to gloss over. Okay. What I will say is that the experiments, the key ones that we're going to do, a lot of times I'm going to find, a lot of these experiments are pretty classical, they're pretty easy to find, and so I've got some videos that sort of highlight what we're going to be doing. I'll link those to the playlist so that when we go down in the lab and do them, it's like, oh, I've seen this. So yeah. And one thing I'll say and I'll keep in mind, when it comes to some of these experiments, I want to be clear. We have a scientific approach that we're needing to follow and that we're needing to adhere to in order to calculate consistent data. Some of them, though, are a little bit subjective, but you also have to understand sort of the overall context and the goal of what we're trying to do. For example, I remember when I was first taking this class and you start looking at the way in the lab that we determine the saturated surface dry condition of a sand, okay? And the way that you do that is you have a little cone, you tamp the cone, you lift the cone, and then once the sand starts to dissipate from the shape, then you know it's at the SSD condition. Is there a little bit of subjectivity in seeing that? Yeah, there is. But keep in mind, I mean, I'm just going to say it, we're not building a space shuttle, we're characterizing sands for inclusion in concrete. We do need some data, but there is sort of it's good enough, a data set. So just keep that in mind in context for what we're doing in here. Okay. Some of the experiments that we're not going to do, but I did sort of want to highlight, is, for example, trying to assess resistance to weathering and its soundness and durability. So, like, the idea is that if you have a concrete that's exposed to the elements and the aggregate accepts water inside the aggregate and then it freezes, freezing expansion cracks the aggregate, that will affect a concrete, its performance over time. And so there is an experiment for what you would do is you would take a sample, you would determine its mass, you would soak it in magnesium sulfate or sodium sulfate for 16 hours, and then you dry it, and then you soak it again, and you dry it, and you do it for a few cycles. Over time, the sodium sulfate or the magnesium sulfate is going to eat away at some of the aggregate, so you can do a % loss before and after. Okay, we're not going to do that, but I did want to mention it as an experiment that might be done on a given project. Another project that might be done is a toughness test or an abrasion test. So what you have is in the lab, you have this rotating drum. You put a sample of the aggregate in the drum, and you would put in the drum this charge, which are basically these big old steel balls, rotate the drum for 500 revolutions. So this is what your aggregate might look like before. This is what it's going to look like after. So measure mass loss and whatnot. So we're not going to do that in here, but it is a test that you might see. If you ever hear anybody talk about a Los Angeles abrasion number, that's what we're talking about. I'm not curious anybody DOH if they ever mentioned a Los Angeles abrasion test. This is what that is. If you ever hear that on a DOH construction site, that's what they're talking about. Okay. If there's any one slide that I really want you to absorb, no pun intended, with this lecture, it's this one, okay? So I want to talk about the moisture states of an aggregate, okay? And again, you got to understand that aggregates are an ingredient for use in concrete, okay? And understanding the nascent moisture state of an aggregate is very important to developing a quality mix, okay? And so this is going to be a lot of what our initial laboratory exercises are looking at, is moisture content. So the idea is that if I go out to a quarry right now, or if I go out to a site right now, and I just get a sample of aggregate, just air dry out in the environment, it's going to have some moisture in it. How much moisture and how we characterize that is dependent upon what I'll call two bounded, maybe what we'll call extreme cases of moisture. So let's start with this one right here. This is dry or bone dry moisture state. When can we achieve this? Really in a lab, okay? So what we'll do for some of our experiments is we will collect some aggregate, we'll weigh it, and then we'll stick it in an oven for 24 hours and weigh it again, okay? And so what I said earlier when I said some of the experiments we're not going to be able to collect all the data right then and there, this is what I was talking about. Because even if we weigh the sample right there in the lab, we'll stick that sample in the oven, we have to wait 24 hours. I can't speed up time or just dry out the sample or cook it any faster than that. And if I could, I would in fact be an Avenger and I wouldn't be a professor. I wouldn't be doing this. Okay. So yeah, I can't do that. But yeah, this is sort of the extreme end of moisture. So in this case, what I'm saying here down here is I'm saying we have W sub S and W sub W. What I'm talking about is the weight of the solids and the weight of the water. And in this moisture state, the weight of the water is in fact 0. Okay? Now, I'm going to skip ahead a little bit and I want to talk about this moisture state right here. This is what's called saturated surface dry. This is probably our most fundamental baseline moisture state for an aggregate. Okay? What I want you to think about in terms of an aggregate is I want you to think about an aggregate like it's a sponge. Okay? So, in this moisture state, saturated surface dry, what I am saying is that all of the pores of that sponge are full of water. But I am also saying that the surface of that sponge is dry, okay? So in other words, this is the state where the sponge has accepted internally as much water as it can, okay? So we'll call this maybe the weight of the solids, and this weight, W sub P, I'm sort of saying all the pores of that aggregate are filled with water, okay? And so the real world is probably going to be either here or here, okay? So what I'm saying is if I go out and I collect some aggregate out in the real world, like let's say on a day like today where there hasn't been a lot of humidity, well maybe a little bit of humidity, but we haven't had rain and whatnot. So the aggregate is, like we go out in the field right now, it's probably, some of the pores got a little bit of water into it, but not all of them, right? Okay. So I would need to understand those percentages in order to properly mix concrete. I mean, think, concrete is a mixture of gravel, sand, cement, and water, okay? But I'm saying the aggregate already probably has a little bit of water in it, okay? So understanding that is key to understanding how much extra water I have to add. Because I'm saying free water, free moisture, is anything in excess of this, okay? So for example, let's just make up some numbers. If the saturated surface dry condition is, let's say, 4% moisture content. So a 4% moisture content is here. And the aggregate actually has a 7% moisture content. I'm saying the voids are all filled and I got 3% moisture content already present. Okay? That's the free moisture that I have. All right, does that make sense? So this is like the worst case, this is the most extreme moisture content we can have is dry when there's no moisture at all. And this is our baseline. And in the real world, we're either going to be here or here. Okay? Does that make sense? Everybody with me on that? Okay. So I'm talking about moisture content. What is moisture content? Okay? Moisture content, by its definition, moisture content is defined as the water weight divided by the weight of the solids. Okay? And by solids, I mean like the rock, stone material, the gravel, the sand, etc. Okay, so let's just think through how would you determine moisture content of a given sample? Well, weigh it, stick it in an oven, weigh it again, right? Okay, so that's kind of what we're talking about here. Okay, now a little bit of terminology here. Okay. So remember how we said saturated surface dry is the baseline for moisture content, and we're either above or below saturated surface dry. So we calculate moisture content or water content by taking the weight of the water over the weight of the solids. But we have a specific name for what is the moisture content whenever the sample is at saturated surface dry, and we call that absorption. In other words, remember, what is saturated surface dry? It's the sponge with all the pores filled, but the surface dry. So that moisture state is when the sponge has absorbed as much water as it can internally. So we call that moisture state absorption. So absorption is the moisture state at SSD, at the saturated surface dry condition. And so the free moisture is just the difference between what the sample actually has versus what's the moisture content at SSD. So if it has negative free moisture, that means the aggregate can absorb more water to fill the voids, but if it has positive free moisture, that aggregate is already going to have moisture on it that goes into the cement paste. So you kind of want to correct for that when you're designing your mix. Okay? Make sense? Everybody okay with that? All right. So just to go back to some terms here, so what is the moisture content or the water content right here? It's 0. There is no moisture content. What is the moisture content right here? Well, it's the weight, so it's the weight of the water over the weight of the solids. But how do we get the weight of the water? We take the weight at saturated surface dry minus the weight when it's oven dry. So the difference between the two is how much water it is at SSD. So this divided by that is the absorption. And so what I'm saying is, again, water content is determined the same way, but it's often compared to this to see whether or not the pores can take on more water or there's excess water in the aggregate. Okay? And I think that the easiest way to work through that is to do an example. So let's do a quick example on this. Again, I think you're going to find this is really pretty easy, okay? Again, context is king here. So let me go to our notebook here. So let's read through this. So what I want to know is, given let's take this information, let's determine the moisture content and the total moisture content and the free moisture content of the following example. Okay, so I have the moist mass and the dry mass. So this is me measuring the weight prior to sticking it in the oven, and then measuring the weight after sticking it in the oven. Okay, so I've got that, and then I also know that this aggregate has an absorption rate of 1.6%. So in other words, it takes a moisture content of 1.6% to fully fill those voids to get it to the saturated surface dry condition. Okay, so let's just take some terminology here. So let's start off with the mass of the water. Okay, now we know from this that the weight of the sample, I'll be honest, I am going to use the terms mass and weight a little bit interchangeably, probably more than I should, but again, it's not really going to be as much of an issue with the context of what we're doing in here. Okay, so we have the weight of the total sample and then the weight of the solids. So just like comparing these two, how would I determine the amount of water, the weight of the water in the sample? How would I do that?
Just do the moist minus the dry.
Yeah, just subtract the two. Okay. Somebody want to help me with that? So 0.3 is something 0.3.
35.3.
I have a second?
Yep.
So that's how much water is present in the sample, okay? So if I wanted to determine the moisture content, okay, and just so you're aware, I do my best to try and standardize things, but I just want to say you might see moisture content written like this. You might see it written like that, but it's essentially saying the same thing. And so the way that we're going to do that is the weight of the water over the weight of the solids, and then we're going to convert that to a percentage. Okay, so we're going to multiply that times 100%. So what that's going to mean is 35.3 grams over 589.9 grams times 100%. Okay, and this is going to equal what?
0.059.
Times 100%?
Yep.
5.9.
No. Did
Yeah.
you multiply by 100 though? You didn't put a decimal. Yeah, because wait. Let me see what you did. Hold on.
My calculator being stupid.
I think so. Oh, if you put the percentage, it's saying multiply by 1. I was just say something right there. Yeah, it's the 1. But that's not a Casio FX115ES Plus or similar scientific calculator. That's your phone. Where is your Casio FX115ES Plus or similar scientific calculator?
Never had one. Come on. No.
Get.
Don't have one.
I'm woozy. I'm dizzy. You need a calculator. All right. What? Now, is it? Hold on. Wait. Is it 8-9 or 9-8?
I got 9-8.
Yeah. The lack of a Casio just messed with my equilibrium. Woo. All right. Do I have a second on this?
Yes.
Okay. All right. So, do we agree that this is the moisture content of the sample as is? Okay. All right. So that is at least our first answer. Now, let's just sort of go through the problem a little bit, and let's see if we can discern what's going on. So we're determining the total moisture content and the free moisture content, and we haven't used this absorption, okay? So the absorption is 1.6%. So I want you to compare these two, compare this and this, and tell me what's going on. Do we have excess moisture in the sample, or do we have voids that can still take on water? Which do we have?
Excess.
Who says excess? Who says voids? It's excess. Because this right here is if the voids are completely full of water, okay? This is how much we have, so there's more going on. So how much excess moisture do we have, okay? So we'll just call it free moisture. How would we calculate that? We would take WC and then do what? Subtract it from A, right? Because that's what absorption is, right? So this is going to be 5.98% minus 1.6%. And what is that? 4.38. Okay. I want to put this value in context. Somebody tell me, what is 4.38% of the weight of the solids? Somebody tell me what that is. 4.38% of 589.9 grams. 25.83. Do I have a second on that? Here's what I'm saying. If I were to mix concrete with this, the sample already has 25.83 grams of water before I even put any in there, okay? So it's that type of correction that we need to make when we develop a mix design, okay? Does that make sense? Is everybody okay with that? Okay. All right, so far so good? Okay. All right. Now with that, let's talk about specific gravity. Does that come up in fluids yet? I'll just say, you should be talking about it soon if you haven't already talked about it. Okay, so what is specific gravity? Specific gravity is the weight of essentially a comparison of a material's density or unit weight compared to that of the density or unit weight of water. Okay. Now, you'll get the same term whether or not you use densities or you use unit weights. By the way, what are the units for a specific gravity value? Like if I said specific gravity was 2.5, what are the units for that? It's unitless. There are no units. Okay. It is a unitless quantity. Okay. So by its very nature, it is a very useful term in engineering computations, the idea of specific gravity. Okay. Okay. Now, the determination of specific gravity of a fluid is a pretty straightforward enterprise. For example, if I wanted to determine the specific gravity of motor oil, how would I do that? Okay, well, get a known volume of motor oil, weigh it, right? The weight divided by the volume gives me a density of the motor oil or the unit weight of the motor oil, compare that to the unit weight of water, and by golly gosh gee, boom, there we go, right? I have myself a specific gravity. But what I am proposing is that the specific gravity for an aggregate is a little bit trickier, okay? First off, okay, the trickiest part to figure out is the volume, okay? Because an aggregate is not a fluid that fills up all spaces. There's big particles and small particles, and there's air particles, and so on and so forth. So that part's going to be challenging. And then the second part that's challenging is the fact that the moisture content of the aggregate itself, is it dry, is it saturated surface dry, whatever. So there's challenges there, okay? So the first thing I want to do is I want to recognize that, okay, the specific gravity is defined as a mass over volume divided by mass over volume, okay? And you should be using the same volume. So we can cancel that term out and really calculate specific gravity as a mass over mass or a weight over weight, as long as the volume's the same, okay? If the volumes were different, we would have to incorporate that. But we can control that in an experimental setting, so we can cancel out the volumes if they're the same. So really what we're comparing is a mass of solids divided by an associated mass of water, okay? Now, that would be pretty straightforward then if it weren't for the voids, okay? So are we accounting for a aggregate with the voids filled, or are we accounting for an aggregate where the voids are empty, okay? And so that goes into these terms bulk and apparent, okay? And we have three different specific gravities that we're going to compute. At the end of the day, they really are plug and chug formulas that are pretty easy to compute. The big thing I just want to make sure that you're aware of is what is bulk and apparent. And I also want you to be clear about the experimental test setup, okay? Now, what we're going to do, this is an experiment we're going to do in here. This is going to be off of ASTM C127. I have a video that shows you how to do the experiment start to finish, and I'll tag that to the playlist here in a second. We're not going to do that experiment today, so I'm not going to worry about pulling it up. But essentially what we're going to do is we're going to develop three different weights. We're going to develop the dry weight, the saturated surface dry weight, and then the weight of the sample when it's fully submerged in water, okay? Now, if you notice for bulk dry, saturated surface dry, bulk dry specific gravities, the denominator, what we're doing is we're taking this minus this, but for apparent specific gravity, we're taking that minus that. And so the idea, here's the idea. When we're using apparent specific gravities, we're assuming that the volume that we care about is the dry volume, but when we're looking at bulk specific gravities, we're assuming the SSD volume is the gravity. So in other words, if we had a particle, let's say we had two particles. Here's a particle and here's a particle. And they both have like a crack here and they have a crack here. So it's the same volume or same particle, okay? With bulk computations, we're using like that volume, but with apparent, we're using that volume. Does that make sense? So that's really the difference there. And so the way that we determine that is we just take the difference between the weight, either dry or SSD, minus the weight submerged, so that we get the weight of the water that occupies that volume. That's kind of the idea there. Okay. Now the way that method works is we're going to have dry aggregate that we then saturate, and by saturate what we're going to do is submerge it in water and then dry the surface. We measure its weight, and then we measure the weight when the sample is fully submerged in water. Then we dry it in an oven, measure the dry weight, then we have our three weights, plug and chug. It's really a fairly straightforward computation. We can also get the absorption by taking the difference of these two divided by the dry. But I mean, we literally just went through how to do that. Okay, for fine aggregate, it's a little bit trickier, so we'll probably pull this video up when we We'll probably pull this video up when we get to that lab, but the idea is that we are reviewing the behavior when we form like this cone. We take the cone, we tamp it, lift. Once the sand starts to fall under its own weight, but still kind of retains the cone shape, we consider that saturated surface dry condition. The only difference is we have to account for the weight of what we call this pinkometer that's also filled with water. Again, I am going to kind of skip over that a little bit because I want to review that in more detail when it's time to do those labs, so that's a little bit more fresh in your head. Okay. I'll say a little bit about aggregate sampling here. Whenever we sample aggregates, we do want to make sure that the samples are random and representative. Now, I'm talking a little bit about this, but I'll say in here, especially for the purposes of time, a lot of times when we do the labs, the samples will be measured out for you, okay? Especially when we do the concrete lab. So the way that we're going to do the concrete lab is there are 6 lab groups in here, okay? Those 6 lab groups are each going to get a different concrete mix that they're going to proportion in the lab. So some of you are going to have a really soupy mix, some of you are going to have a really dry mix, and everything in between, okay? But when you get to the lab, the gravel, sand, and cement will be weighed out for you. The only thing you're going to have to figure out is the water, okay? So we'll get to that when we get to it, okay? But for the purposes of sampling, you just want to make sure your samples are random and representative. So you know you might take that sample from a stockpile and then use like a sample splitter or a method of quartering that sample, and then, for example, you'll quarter the sample and discard these 2 and use these, or use a sample splitter and only use half of it. Again, you want as little of human influence over the sample that you're actually testing. Okay. I'll skip over this quite a bit. You just want to make sure that you're not mixing samples, obviously, that the samples aren't being contaminated, you're not dropping them from large heights, that you're moving them carefully. I mean, why would dropping from big heights being an issue? Because you don't want to degrade the sample. You want to test the sample as is, and so if it dropped, you might break some particles, and then you're screwing up what you were trying to assess throughout the process. Okay, so let's talk about this unit weight computation. Ultimately what we're going to be computing is a weight over volume. Again, the big issue is what exactly is the volume. And I really kind of like this slide here because it kind of makes the point that what exactly is the volume? You know, is it loose, is it compacted, is it so on and so forth? Okay. What we're going to do, I mentioned this because I've got loose and compacted aggregate in the lab today. So the loose aggregate is basically, for the lab that we do today, it was basically just placed in a container as is, no sudden drops, struck off the top, that's the aggregate. So for the compacted aggregate, the idea is that we place the aggregate in the container, but we use a tamping rod and we tamp it a certain number of times. We typically tamp it 25 times in 3 lifts, and that shakes out the air voids in there and allows more aggregate to fill the container. So I mean, without doing the lab and out giving you too many hints, which do you think is a heavier box, a dense aggregate or a loose aggregate? Dense, because it fills more material. So that should be a pretty straightforward determination to make. Okay. Now, what we're going to focus on, at least for us, is dependent upon a given source of aggregate. We want to see not only how much of that in a given volume, how much of that volume is filled by solids, but how much of it is filled by voids. And we can do that by accounting for the specific gravity. Okay. Now, the way that you compute specific gravity, again, is you can take the weight of the sample divided by the weight of the water. Let's talk about how we would figure out percent solids and percent voids. So let's just work through that in our head. Okay, so let's say we had a given sample. How do we figure out how much of that sample is filled up by solids? Well, we would take the volume of the sample divided by the volume overall. multiply by 100%. So I'm probably going to stop saying multiply by 100% because I think you can probably follow along with that. Now both of these, again, a unit weight is just a weight divided by a volume. So I can replace, for example, the volume of solids divided by weight over gamma, but essentially the gammas are different. Because in this case, it's the unit weight of the solids. In this case, it's the unit weight of the entire sample, that bulk unit weight. So by comparing those two unit weights, I can get the percent solids. Okay, easiest way to work through that is to go through an example. And let's do that one real quick before we go down to lab. And I think you'll find this is a pretty straightforward enterprise. Okay, so what we're going to do is we're going to determine the, let me pull this up here. We're going to determine, for a given sample, we're going to determine the bulk unit weight and the percent volume of voids. And I think you'll find this is a pretty straightforward process to do. So we're going to have the volume of a mold and the tear of a mold. Does anybody know what I mean when I say the tear of a mold? Okay, a good example of that is this right here. Okay, so in other words, we have a box, right? That box is filled with coal. We weigh the box, we get a number. We have to subtract the weight of the box to get the weight of just the coal. Okay? So if I ever use the tear, what I'm talking about is the weight of the cup or the mold that's containing the sample. Okay? Because ultimately we don't care what the weight of that is. We're talking about the weight of the sample. Okay? So more often than not in any computation, you're going to have to subtract off the weight of the mold to get the actual weight of the sample. Does that make sense? Okay. So I have a mold that has this volume and this weight. What I've done is I've weighed both this and this together, and I know what the bulk specific gravity is already. Okay. So let's see if we can reason through this, because again, I think you'll find this is a pretty straightforward computation. Okay. So let's see if we can work through this first part. Okay, let's see if we can work through this. Okay. All right. Now the bulk unit weight, which we'll call gamma sub B, okay, is essentially just going to be computed as the weight of the solids divided by the volume. I mean, again, this is just a unit weight. It's weight over volume. Okay? All right, so let's see if we can work this out. All right, what is the volume? The volume is going to be what? A third cubic foot or something like that? Is that a fair statement? Okay. Now, what is the weight of the solids? How am I going to figure that out? Well, what do I know? I know that the weight, so I've got this, so think of this mold, let's just say it's a bucket, right? I know the bucket weighs 21 pounds, and I know when the bucket is filled with aggregate, and I weigh the bucket and the aggregate, I get 59.2 pounds. So how do I figure out the weight of the aggregate? Pretty straightforward, right? So this is going to be I think I can do this one in my head. What's that, 38.2? Does that make sense? So therefore, so essentially what I'm doing is I'm just taking 38.2 and what am I doing? Multiplying it by 3. You know, you divide by a third, you're multiplying by 3. What is that multiplied by 3?
114.71.
And we'll say that's pounds per cubic foot. Does that make sense? Does that sound good? Typically, aggregates are going to be in like the 110, 120, 130 range, something about like that. So, sound good? That should be easy. Right. Okay, that should be easy. Now, the next question is going to be, okay, that's great, but how much of that is solids and how much of that is voids? Okay? Well, that's where we can use the bulk-specific gravity. Okay? So, what I'm going to do first is I'm going to say the percent volume of solids. Okay, so here's how we're going to work this out. Okay, so we know that this is 114.71 PCF. Does anybody remember what the unit weight of water is? Yes, 62.4 pounds per cubic foot. That's how heavy, if I give you a box of water, that is the unit weight of water. Okay? All right. And I am giving you the bulk specific gravity of 2.63. Okay? All right. So let me see if we can work through the logic here. Let's see if we can work through the logic here. All right. I'm going to take these two. Let's take these two and multiply them together. Okay? What do we get when we do this? Say it again? 164. Do I have a second on that?
Yep.
All right. Now, okay, I want to think about this value and what this value represents. Okay, whenever we use a bulk-specific gravity, or even if it's an apparent-specific gravity, what we're assuming, so what this value represents, okay, this value represents if we had a sample that was absolutely, completely filled with aggregate. Like, not individual particles. We're talking like a solid hunk of stone that was comprised of this material. Okay? So here's what I'm saying. I'm saying that if we had a solid hunk of stone comprised of this material, this is how much it would weigh per cubic foot. Okay? Everybody with me on that? But I'm saying that we went and weighed a sample in the lab, and this is what we're getting. Okay? So here's my point. If I were to take the ratio of this and this, let's see if we do that. Let's do that. So therefore, let's do that. Here, let me formalize that a little bit. Let's take the ratio of these. What do we get here?
1.43.
What's that?
1.43.
That's not what I'm getting. I'm not getting that. I'm getting something else.
69.94.
Do I have a second?
Yes.
Okay. Let's think about it like this. Let's think about it like this. Let's keep the math simple. Okay? Does everybody agree that this number right here is how much the sample would weigh if it was a solid hunk of stone? Right? Now let's say we went to the lab and we calculated this value and it was in fact 164. What that would mean is that the percent volume of solids will be 100%. If it's 100% solids, how much voids are present? Zero. Okay? Now what I'm saying is that we calculated this is our unit weight. Okay? So what I'm saying is this is how much the unit weight is if it's totally solid. We calculated this. So if we take the ratio of these two, we get about, the sample is about 70% rock, right? And if it's about 70% rock, how much is it voids or air?
30.
There you go. So how do we get that? What's that?
The hundreds minus.
100 minus that. Okay? So what I'm saying right here is that this term is the percent volume solids. Therefore, the percent volume voids is just minus that. Okay? Does that make sense? So this is going to be 30.06. Did I get that right? Okay. Ultimately, what the point I'm trying to get at is I'm trying to get you to characterize and think about, given a material, how do we characterize that? What are its weights? What are its specific gravities? How much volume is it occupying? How much volume is solids? How much volume is voids? And so on and so forth. Okay? I'm doing that really for two reasons. One is, number one, I am trying to... we're going to see these terms later in this course when we look at concrete and things like that. But number two, you will see these terms in other courses as well. For my geotech folks, does anybody remember what happens if you take the volume of voids and you divide it by the volume of solids? You get a term. What's that?
Void ratio.
We also term that the porosity. Does anybody remember that? What's that?
I remember void ratio.
Okay,
That one.
if you remember, but porosity and stuff. Okay. Does anybody have any questions? Okay. All right. So let's recap some housekeeping items before we go down to the lab. Okay. What's due Thursday? Homework 1. Okay. We're going to have 3 exercises in lab, right? First exercise, we look. Second exercise, we lift. Third exercise, we record. And remember, when you record, do like a value minus 11 to account for the weight of the box. I weighed the boxes, they weighed about 11 pounds. Okay, tell you what, give me like a minute or two to break down my computer and we'll all head down together, okay? All right.